So back to conservation of energy. This video, I want to start to discuss the math behind the concept of conservation of energy. And again, remember we're talking about things that are rising and falling. That's what we'll deal with first. Then we're going to look at a pendulum. I spelled that wrong in the first video. And then we're going to look at a roller coaster. So the first thing is something that's rising and falling. I need to tell you, we're going through this particular process just to understand what's going on here. But this isn't really how the problems will look. They'll look more like this one down here, and we'll do this one. So this says a 0.4 kilogram cat is thrown upward at 15 meters per second. We still need to draw a picture. Cat's thrown upward. Picture looks like that. EI at the bottom, EF at the top, initial and final. Remember, we're not using zero for any energies. It's either potential, kinetic, or both. Whenever you do EI and EF, you must then decide which type of energy it is. EI at the bottom is kinetic because the cat is being thrown. And this point down here at the bottom specifically is referring to the instant when the cat leaves your hand. And it hasn't gained any height yet, or whatever you're throwing, ball or whatever it is. If it's something that's falling, then that point at the bottom is the instant right before it hits the ground, again, with no height. At the top, it's all height and there's no speed because whatever you throw upward will come to a stop at some point. So that will be all potential energy. So everything at the top is potential, everything at the bottom is kinetic, and everything in between will actually be both forms of energy. So what this wants us to find is potential, kinetic, and total energy immediately after it's thrown, which is down here, at a height of 3 meters, which is somewhere in the middle. Doesn't have to be exactly in the middle, but somewhere in the middle. And at the top of its flight, up here at the top. So at each of these points, I just want to go PE, KE, and total energy. I'll pause the video and come back when that's all done. And we're back. So on the first one, immediately after it's thrown, I want to know potential, kinetic, and total energy. Well, I said already that the height down here is 0. It actually hasn't gained any height yet. Therefore, the potential energy at the bottom has to be 0. And I would put in parentheses because the height is 0. It's the reason why there's no potential energy down there. Kinetic energy at the bottom, keep in mind, we can either use the equation to find the energy or subtract from the total. We know the speed. We know how fast we're throwing the cat. It's 15 meters per second. So we can do mv squared over 2. The mass of the cat is 0.4. Again, speed is 15. Don't forget to square it over 2. And if you do 15 squared, remember you have to do that first. 15 squared times 0.4 divided by 2, you should get 45. 45 joules is the potential, kinetic energy. And then total energy, remember, total energy is potential plus kinetic. If we add these two, we simply get 45. And this is really useful because the law of conservation of energy says that the total energy remains the same. So now that we know what the total energy is at the very beginning, that has to be the total energy of this cat for the entire flight because it's a closed system. No energy is coming in or going out. So I'm going to put 45 joules for the total energy for all the rest of for both of the other two. It has to be 45 everywhere else. The next point, we know the height is 3 meters. So the potential energy there, we can do mgh for potential energy. That's our formula for potential energy. Mass, again, is 0.4. Our g is the acceleration due to gravity. That's 9.8. And here's our height, 3 meters. 0.4 times 9.8 times 3 gives us 11.76. That's our potential energy at that particular point. Okay, so now all we have left is the kinetic energy here. Before, we did mv squared over 2. The problem here is we can't do that, though, because we do not know the speed at that point. If we throw the cat up at 15 meters per second, we know that the speed is going to decrease on the way up. It's somewhere in the middle. I don't know exactly where, but I don't know what the speed is there. It's not 15. It's not the speed that they gave us. Since we do not have the speed, we can't use the equation to find the kinetic energy. The only choice we have here then is number 2. We're going to subtract from the total. So we know the total energy is 45. and we found that 11.76 joules is the potential energy. So what's left has to be kinetic energy, because remember, the total has to stay the same. If you subtract those two, you get something like 33.2. So the kinetic energy there has to be 33.2 joules. So we can see the kinetic energy decreased from 45 to 33.2. Potential energy increased from 0 to 11.76. That's exactly what the graph looked like that we drew in the previous video. And then the last one, at the top of its flight, well, what happens at the top? Speed at the top is 0, which means kinetic energy is 0. And potential energy, I don't know this height up here. I have no idea how high it's gone. We're going to find that right here. But even though I don't know how high it's gone, I know that the potential energy has to be 45 joules, because that's what the total is. It still has to have that much energy at that point. And at that point, all of the kinetic energy that it had at the bottom has been converted into potential energy. Now we can use that to find out how high the thing went using the potential energy formula, mgh. We know that 45 joules is the potential energy. I know the mass is 0.4. Again, g is 9.8. I'm going to solve for h. 0.4 times 9.8, if you multiply those two, you get 3.92. Algebra here, divide by that, and we get 11.5 meters for the height. That's how high the cat went, which is a crazy problem. That wouldn't actually occur, but that's how to do this. If we draw this graph, it's going to look very similar to the one that we've drawn earlier. If this is 45 joules and this is 0, just go ahead for a minute, and I want you to draw a line for total energy, draw a line for potential energy, and draw a line for kinetic energy of this cat, of this particular cat right here. Draw the 3 lines, pause the video, and see if you do it right. Alright, so like we did before, total energy, straight across. Stays the same, it's always 45. That's the easiest one to draw. The next easiest one is potential energy. Potential energy, we said, follows the height. We'll say that over and over. Cat's height increased, potential energy increased. Kinetic energy is the last one we draw, and it's also very easy because kinetic energy must be the reverse image of potential energy, because they both have to add to 45. So we draw kinetic energy here, and that's the way our graph looks there. Okay, so the reality is the problems are not going to be stated in this way. This is a very easy problem to think through, but really what's happening is with this problem right here, with problems that read like this, what we're going to do is take all of this and sum it all up basically in one small statement in one small math problem. So here we have a wedge of cheese being dropped. I don't know why you would do that, but that's what's happening regardless. From a height of 22 meters. So there's our height. Cheese is being dropped. EI at the top, EF at the bottom. You must draw pictures with these problems. If you don't, you're probably not going to be on the right track. And when you draw a picture, you must make a decision about what kind of energy is happening at your EI and EF locations. At the top, it's all potential energy. At the bottom, there's no height left. This is just before it hits the ground. The potential energy has been converted into kinetic energy. And we'll kind of put a lot of that together in just a minute. Okay, so we know this. We've drawn the picture. And we know that the law of conservation of energy says that however much energy we have here, it has to be the same here. And that's what happened in this problem. We had 45 joules of potential energy here. We found we had 45 joules of kinetic energy here. So whatever happens with conservation of energy, anytime you have these 3 types of problems, the problem will always begin this way. It will be a closed system, and in a closed system, this amount of energy has to be the same as that amount of energy. So we start by saying EI equals EF. What flows from this, what we write next, is determined by the picture that we drew. So if you don't draw a picture and make these decisions, you cannot do the next part. You can't do it. We said that EI, we made the decision that the initial energy state is potential energy only. And the formula for potential energy is mgh. So that's what's going to go underneath for EI. EF, we decided, was kinetic energy. So we're going to put in the formula for kinetic energy, mv squared over 2, and they are equal to each other. These decisions don't come out of thin air. They come from the decisions we made based on reading the problem and understanding what's going on. This is the math that's going on here. And they want to know how fast it impacts the ground. Typically, at this point, what we would do is plug in numbers and solve for what we want to know. We want to know that v. Whenever you solve for something, you have to know everything else in the problem and plug it in. We know that g is 9.8. We know that it's starting at a height of 22 meters, but the mass is not there. So here's the question. If you have a wedge of cheese, let's say 2 of them, one of them weighs 100 pounds, or let's say has a mass of 100 kilograms, and another one has a mass of 5 kilograms, and you drop them in a closed system, which one will hit the ground faster? You might think the heavier one will hit the ground faster, but if you think back to the beginning of the year, we did an experiment that proves without air resistance, they will both hit the ground at the same time and at the same speed because gravity affects all objects the same regardless of their mass. That means, practically speaking, mass doesn't matter. And if we look at it algebraically, I can actually divide by mass on both sides and m will actually cancel out. That happens every single time. So I want you to pay attention here and star this point in the conversation. As long as you're starting this way, with all conservation of energy problems, you will have a mass on both sides. Sometimes they'll give you the mass, like they did with the cat. Sometimes you won't have the mass. You never, ever need it. You can put the mass in there if you want. If you do all the right math, you'll get the same answer as you will without putting the mass in because mass cancels out. It doesn't matter. So since we don't need the mass, we can proceed from here and substitute everything else in. Our g is 9.8. We know our height was 22 meters. We get it from right there. Mass is going away here. V, I don't know. That's what I'm trying to find, so I'm going to leave it as a V. Don't forget the squared. Don't forget over 2. Solving for V now. So I got to get rid of the squared, got to get rid of the 2. I'm going to start with the 2 by multiplying by 2 on both sides. It gets rid of it here. Times 2 over here. 2 times 9.8 times 22 gives you 431.2. Still left with v squared on that side. Got to get rid of the squared. Take the square root. Square root of 431.2 is 20.8. That is our answer. If you drop a wedge of cheese or anything, it doesn't matter what it is and it doesn't matter how much it weighs, as long as it's a closed system and there's no air resistance, you drop it from a height of 22 meters, it hits the ground at 20.8 meters per second. So if you didn't follow that, go back and in the video where I started it and try to go through it again, see if you can follow everything, make sure you understood where everything is going. Once you're satisfied with that, let's go ahead and go to the top of the next page. And on this page we see a picture of a pendulum and we see a picture of a roller coaster. 2 pictures here. What I want to do first is I just want you to think about each of these 4 positions with the pendulum and with the roller coaster. A couple things you need to know about a pendulum. First of all, when you see a picture of a pendulum, you can assume that the 2 outermost points, or maybe there will only be one shown, but the outermost point is at the highest possible point for the pendulum. It's at the highest possible point. The other thing you can assume is that the position right in the middle, hanging straight down, is at the lowest possible point in the pendulum. Okay, and out here the pendulum stops for a minute. The speed is 0. At the bottom the height is 0. It cannot go any lower than that, so we're going to consider the height to be 0. So what I want you to do right now, knowing that, 4 positions for the pendulum, 4 positions for this roller coaster. I want you to decide what type of energy is present at each of those 4 locations in the pendulum and in the roller coaster. Again, keeping in mind your choices are potential, kinetic, or both. What type of energy is present? Pause the video now and make those decisions. All right, if you had a hard time making those decisions or are having a hard time, there's really only 2 questions here. With potential energy, you ask yourself, is there height? Kinetic energy, you ask yourself, is there speed? It's very, very simple. The answers to those questions will lead you to that point. So at this point, Does the pendulum have height? Yes, it does. So it definitely has some potential energy. Does the pendulum have speed at this point? The answer is no. At the outermost point, the pendulum will stop for just a moment and the speed is 0. Therefore, right here, potential energy is the only thing we have. Might even want to write speed is 0, same on the other side. So this one over here will be potential energy as well. It's the same on either side. Let's go to the one at the bottom. This is at the bottom of the thing. Height is 0. So the questions, is there height? Answer is no. There's no potential energy. Is there speed? These are not, these balls at this position are not still. These are like snapshots in time of a pendulum that is actively swinging back and forth. So is there speed here? Yes, there is. As a matter of fact, that's the highest speed in the whole thing. It'll slow down on the way up. It'll speed up on the way down. So there is speed here. It's got to be all kinetic energy, no potential, because there's all speed and no height. Here we had all height and no speed. In the middle, does the pendulum have height? The answer is yes, because it can fall lower than it currently is. So there's got to be some potential energy. But does the pendulum have speed? The answer is yes, it does. It is certainly moving here. It will be going faster. That's not the fastest point. But it is moving there, and because it is moving, it does have kinetic energy. So this is that special place where we have both forms of energy, because there's both height and speed in the same place. Let's go ahead and go to the bottom and talk about the roller coaster. At the top of the roller coaster, this is the point where right before they let you go, they give you a second and they stop you so that you can reconsider your decision to ride that roller coaster. Since you're stopped, there's no speed at the top. At the top of the roller coaster, it's all potential energy because you definitely have height there. The roller coaster is funny. At the bottom, at the top and the bottom, it's easy. At the bottom, we know that the height is 0. There's no more height, but it's certainly moving at the bottom. It will come back up to the other side. So since there's no height, there's no potential energy, but it is moving, so there is kinetic energy. So potential at the top, kinetic at the very bottom. These two right here. This point, is there height? Certainly there is. I'm going to write down potential energy. Is there speed? Certainly there is. The roller coaster will be moving. So this is a point where there's both height and speed, therefore both potential and kinetic energy. Both forms of energy there. This one is the hardest one for students usually. Many students will simply say potential energy right here. And the reason they say potential energy is because this was the top of a hill. Therefore, since this is the top of a hill, it must be potential energy. With a roller coaster, resist the temptation to look at what the roller coaster looks like at that point. It is all about simply what I wrote up here. Does it have height and does it have speed? Period. If it's all potential energy here, then the question is, how much kinetic energy does it have? And the answer to that question would be 0. And if it has 0 kinetic energy here, that means the speed would be 0 and we stop. We cannot finish the ride. Maybe we even fall back down. Which is obviously undesirable. We wouldn't want that. It's got to be moving there. It's got to have potential energy. So let's just go back to our questions. Does it have height? Yes, it certainly does. Does it have speed? Yeah, it's going to be moving at that point. It's going to be moving, so it's got to have both potential and kinetic energy there. So here's what I want you to know to sum all this up. The 3 types of problems were anything that is thrown up in the air or falling. We had pendulums that we just talked about. And then we also have roller coasters. Those 3 types of problems. It doesn't matter what kind of problem it is. Check it out. Something rising and falling. Everything at the top was always potential in both of those problems we did. Everything at the bottom, always kinetic in both of the problems we did. It doesn't matter which direction it's going. And everything in the middle is both types of energy. Everything at the top is potential. Everything at the bottom is kinetic. Everything in the middle is both. Check it out. Pendulum. Everything at the top, potential energy. Everything at the bottom, kinetic energy. That's what we decided up here. And everything in the middle is both. Same thing. Everything at the top, potential. Everything at the bottom, kinetic. Everything in the middle is both, regardless of what direction it's going. Roller coaster, everything at the top, potential energy, the very top. Everything at the very bottom, kinetic energy, which for us in that last problem included both of these places. They're both at the very bottom, at the same place. Everything in the middle, though, everything in the middle, regardless of what the roller coaster looks like, whether it's going down, whether it's going up, whether it's the top of a hill, or I'll show you another one in a minute, everything in the middle is both forms of energy, both potential and kinetic. Look at this roller coaster. Look how I'm going to change things here. What about this point right here? What kind of energy now? See, many people will say, oh, that's kinetic energy. No, it's not. Everything at the top is what? Potential. Everything at the bottom is what? Kinetic. And everything in between is both. It does not matter what the roller coaster looks like. Down or up, top of a hill, bottom of a hill, it doesn't matter. Everything in the middle has both forms of energy. Now, I want you to look at this roller coaster real quick, and I want you to think about something. Position 1, 2, 3, 4, 5, 6, and 7. I want you to pause the video for just a minute and think about, if this is a friction-free roller coaster, where in this roller coaster ride are we going to find the most energy? So if you've thought about it, a lot of people say 2 or 3 or 6. The answer is 7. The answer is 7. We find the most energy at 7 simply because at 7, that's where the most kinetic energy is, and it's where the least potential energy is. There's no potential energy here because the height is gone. Many people will say 6 because they say, well, it's going downhill at that point, and then sometimes I draw the lines steeper. If you choose this, the question is, what happens to the speed on the way down the hill? It increases. So if the speed is increasing, it's got to be going faster here than it was here, right? Which means 6 is not the fastest point. It has to be 7. The lowest possible point is where we have the most kinetic energy, and that's where we get the highest speeds.